Okay, here we go. Silly things to cover today, but you know, it is what it is. Derivatives of inverse functions. So we talked about inverse functions. I have a little bit of review built into this from when we talked about inverse functions, and then we're going to get after it. I'm not a big fan of this lesson. I'll explain why as we go along, but it is something we need to cover. We need to cover it only because there's probably going to be like one question on the test that might represent that 1 point that will bump you up into the 5 category. If I didn't cover it, I would feel guilty. I'll get over it, but we should still probably talk about it. Okay, so we're going to talk about inverse functions again. We did this already, but we'll review on that. What makes an inverse function? The other thing we talked about in the past, which again we'll refresh right now, is that all functions have inverses. Not all of those inverses are functions. And then we're going to find the derivative of all those inverse functions. And once again, staying with the healthy theme, you should eat some healthier foods. Okay. Just saying. Okay, so this is one of the first things I don't like. You know already I'm not a big fan of memorization, but there's really no easy way around it here. I could show you the process and explain the process of where these come from, but A, you don't care, and B, it's not helpful. But I will give you some tips here. The stuff that we did when we were doing a derivative of trig functions also apply here. Look at, for instance, the value for the inverse sine versus the value for the inverse cosine. Remember we talked about cofunctions, right? You have a sine function and then you have its cofunction, which is the cosine. They're identical, it's just that the cofunction has a minus sign. So don't go home and memorize 6 things, memorize 3 of them. And you probably don't even need to memorize them. As you do the problems, you'll just get more comfortable with it. And then the other 3 are just the cofunctions have a minus sign in front of it, you're good to go. Okay? And I know you have the slideshow, so you don't have to write this down, so I'm just going to move on to an example here. Okay. What is the derivative of 1 over the inverse sine of x? Okay. So, y prime is equal to the inverse sine of x squared over the inverse sine of x times 0 minus, big honkin' bracket, 1 times the derivative of the inverse sine of x. Well, what's the derivative of the inverse sine of x? You go back to the little chart there, and the derivative of the inverse sine of x is that mess. 1 over the square root of 1 minus x squared. Clean that up a little bit. Whoops, I forgot that. That goes away. Now, this would be bad. Eventually, this will be bad. For now, I don't care. But eventually, we're going to have to get rid of that fraction within a fraction. So this would become, let's see. Well, depending on how you like to get rid of fractions within fractions, I like to multiply by the denominator. And this would become negative 1 over the square root of 1 minus x squared times the inverse sine of x squared. Side note, please tell me you know what this means. Okay, you know that, right? Somebody showed you that? Did anybody not? Okay, these are equivalent statements. All right, good. So we'll flip back and forth between arc sine and inverse. They're the same thing. And honestly, these problems are kind of boring. I will show you one more, and that is this guy. Now, things get... let me back up. We started with something fairly easy, the power rule. We spent a bunch of time taking the derivative of things like 2x cubed. And you practiced, and it became very easy. And then I threw something new at you. Okay, now do a product rule. That became a little bit more challenging, but you practice it. And then I just keep throwing new things at you and combining those things. So if you haven't already noticed here, I've got 3 things combined, I think. There's a product rule in there. You see that? Yes. There's an inverse trig derivative. You see that? Yes, because there's an arc cosine staring at you. And then there's a chain rule. You see that?
Oh, no.
This is going to be fun, right? Okay, great. I'm going to do it in blue this time because I can. Y prime is equal to the arc cosine of the square root of x plus x times. Okay, well, what's the derivative of arc cosine? Well, the derivative of arc cosine is the same thing as the derivative of arc sine with a minus sign in front of it. So minus 1 over the square root of 1 minus x squared. However, I need a chain here. 1/2 x to the negative 1/2. Whoops, I screwed up. This should be a square root there. Oh, that's ugly. Hold on. This should be minus the square root of x quantity squared. Okay. Do you see why it's the square root of x? This is the audience participation part of the program? Yes, okay, good. Because we're dealing with, instead of just dealing with x, we're dealing with a u. And that u is the square root of x. Could you simplify that? Well, sure. I can move the x up on top. I can move the x to the negative 1/2 to the bottom. I move the 2 to the bottom from the 1. I can do a lot of things. But again, at this point, I don't care. We'll get to that later when we start simplifying. That in itself will be a challenge. If you ignore even all the calculus, just doing the algebra of simplifying these trig equations, or not trig equations, calc equations, will be challenging. Okay, we good? Not the most exciting thing in the world. So let's move on to something a little bit more interesting. We did this already. The domain of a function is the range of its inverse. The range of the function is the same as its domain of the inverse. And then this guy at the bottom is important. You put the inverse into the function, you get x. You put the function into the inverse, you get x. They cancel each other out. Okay, good. So we talked about that. And did we talk about graphically inverses? Yes or no? I don't remember. Yes? Okay, well, I'm going to review it again. So I've got this function f, it's in blue, and I've got its inverse in green, f inverse, and the line y equals x. The reflection of a function over the line y equals x graphs its inverse. And if I have a point on the function xy, then it has a corresponding point yx. I'll talk about the maroon lines later. Okay, but we did this already. I think, yes? You tell me yes, so I'm going to go with it. Okay. That's going to be crucial in what I'm about to do. I'm going to show you how to take the derivative of an inverse function in 2 different ways. Why 2 different ways? Because one might make more sense to you, and I want to give you as many tools as possible to make your life as simple as possible. I always prefer a graphical approach. So when I do it my way, I'm going to come back to this model. However, there is a formula. So for those of you that are memorizers and want to just go home and memorize a formula, you can. Okay? So here we go. Here's the formula. If I want to take the derivative of the inverse, okay, so where's my pen? If I want to take the derivative of the inverse of some value x, I get that formula. Well, that's a typo. Not as fan of this. That's supposed to be an Not a fan of this one. That's personal preference. If you want to use the formula, by all means, go ahead. I'll show you what the formula looks like in a second. We'll do that one first. Then I'll show you the way I attack the problem. And I'm not saying my way is better. It just works better with my feeble little brain. Okay? So, let's start with this function. I've got a cubic. And I want to know what is the value of the function when x equals 3. The value of the inverse when x equals 3. Okay. In other words, I've got some inverse here that has a point on it, 3, question mark. I would like to know what that question mark is. But I don't know what the inverse is. So I'm going to approach it a different way. And this is kind of the linchpin to solving these problems. If 3, question mark is on the inverse, what's its corresponding point on the function? Good. So on f of x, we've got some point question mark, comma 3. Knowing this, how do I find the question mark? Louder, prouder.
Plug 3.
No.
Set the function equal to 3.
Good. Set the function equal to 3. Okay. If we had this with the function, you plug 3 in. If we have this, we set the function equal to 3. Okay. So 3 is equal to 1/4 x cubed plus x minus 1. Now, here's where I argued with myself a little bit. I chose a function that's not easy to solve. I could have done a quadratic. I wanted to do a cubic for a variety of reasons which we don't need to go into. And so you're going to have to trust me on this one. Solving that for x. When you're doing inverse problems like this, your x value will always, I shouldn't say always, will commonly be something nice. So you'll just have to trust me on this. I'm telling you that x is equal to 2. If you don't believe me, check it. Because 2 plus 2 is 4 minus 1 is 3. Okay? Which means that the point 2 comma 3 is on the function, and the point 3 comma 2 is on the inverse. Okay? Haven't done and
How would you actually solve for x?
Well, there's a couple ways you can do it. You can pick up your calculator, which would be cheating. You could use Desmos, cheating, or probably synthetic division. But even synthetic division is a guess and check process where you pick a number, see if it works, and go from there.
Yeah, there's a problem like that.
Oh, yeah, that's good. How'd it go?
I don't know how to do it.
I probably don't either.
Come back.
Okay, let's go. We'll come back to that in a second. Okay, so we got this. Haven't done any calculus yet, because now we're going to segue into part B. All right, I want to know the derivative of the inverse at 3. So, we did that already. Good, we got our points. We're all good to go. So, that means if I plug and chug into the formula, if you're a formula person, you would get something like this. All I did in this case is I took that formula that was in the brown box and I stuck in 3. Well, what is f inverse of 3? We did that. It's right there. F inverse of 3 is 2. So this guy became f prime of 2. F prime of 2 you should be able to find because you're all smart fellers. Take the derivative, plug in 2, and you get your answer of 1/4. Okay? Any problems there? Now, some of you might like this process. Great. I'm not belittling it all. It is a valid way to approach the problem. I like to take a different approach. Questions on this before I move on to the graphical approach? Okay, so in order to use the graphical approach, you got to remember one other thing, and that is the stuff in red. The slope of the tangent line, of any tangent line on the original function, is the reciprocal of the slope of this corresponding tangent line on the inverse. Okay, now notice I said reciprocal, not opposite reciprocal, not flopposite. It's just flip it over. Okay? So graphically speaking, we go back to this picture, and you'll notice here's the tangent line. L1 is the tangent line to the function. I lied. L2 is the tangent line to the function. Therefore, its reflection takes me back to L1, which is the tangent line to the inverse. These two slopes are reciprocals of each other. Okay, so the way I approach the problem is I try to stay away from the inverse. I don't want to find the inverse. I don't want to do anything with the inverse. All I need to do is if I'm given this point on the inverse, no, that's on the function. If I'm given this point on the inverse, I want to find its corresponding point on the function. I did that already. Then all I do is find the slope of that tangent line. If I can find the slope of that tangent line, which I can, I'm pretty good at derivatives, I can plug in a number, I take its reciprocal and I get the slope of that puppy. Okay, so it looks something like, let me get some working space here. It looks something like this. I know that the point 2, 3 is on the function, so I'm going to find f prime of 2, 3/4 x squared plus 1. Plugging in 2 there is 4 is 3 is 4. And therefore, f inverse prime of 3 would be 1/4, the reciprocal of that. You'll notice they look very similar. Notice the work that I have there compared to the work that's at the bottom there. It's the same work. I just think of it in a different way. It's entirely up to you which one you want to use. This is not a very common type of problem that shows up. But it is something, like I said, you need to see. Either one of these are probably 1 or 2 questions on the test maximum. But again, if I didn't show it to you and if we didn't practice it, I would be doing you a disservice. Questions? Which one, just right now off the cuff, which one do you think you're more likely to use? How many people would use the equation more? Raise your hand. How many people take the graphical approach? Interesting. It's about 50%. Okay. We're done. Told you, quick, easy lesson. This, discard, stop this.